Let's do an example of a compensator design for tracking a command signal, doing a case like that. All right, so for this case, let's not have a disturbance. So we will have W of t equals 0, so no disturbance present. So the things we need to know for our problem, if we're going to design a compensator block for this problem, is what is our GP? So let's say we have a GP of s that's given something simple like a 1 over s minus 10. And you can see that this is an unstable configuration. If we examine the pole here, we have a pole at positive 10. Okay, so we know that that's in the right-hand plane over here at 10, and therefore it is unstable. Okay, the other thing we need to know is the block configuration. I'm going to say let's use the standard block configuration. For the system. And once again, that is just our usual configuration of having this GC, GP, our output Y over here, the negative feedback. We've drawn this many times. With our reference input coming in here, and it is added in, so just like that. That is our standard configuration. Knowing this gives us what GCL is, and it also gives us what the QCL is. So you remember that GCL is a polynomial PCL over polynomial QCL, and that QCL is very important because that is our characteristic of our whole system. That tells us the stability. Okay. So, is there anything else we need to know about this to get started? And I think we have all the pieces. Okay, so that's our problem. Let's get started designing the compensator block. Okay, so first thing we might want to look at before we get started is how many free S's are we going to need, or do we need any? So we have kind of adhered to the design that if you are designing to track a command signal, you're going to need 2 free S's. And that is really just because we want to be able to at least track the position and velocity of our command signal. And that's pretty good. You could make it even better if you added more free S's, but for our class, for our problems, 2 free S's is what we're going to stick with. We need at least that. And since we don't have a disturbance, we'll not need any additional possible free S's. Okay, so now let's look at GP, see if there are any given to us. And in this case, we don't have any free S's given to us by GP. So what we can do is just take our trial designs, and let's write that on another sheet over here. So we're going to come up with some trial designs for GC of S. And we know that we will need 2 free S's included since we are not given any in our GP. Okay, so let's come up with those trial designs. All right, so we'll start off with a KC over S squared. There's our free S right there. And that'll be our first trial design. If that doesn't work, we can increase the complexity, and we're allowed to add to the numerator, in this case, because we have 2 S's on the bottom, we can add a term up here. So this will be our second trial design. we'll do one more, and hopefully by the third trial design we have something that works, at least by that time. Okay, and we can again increase the complexity on the numerator in that case. So remember, I really don't want to increase the complexity on the denominator. I don't want to add another s down here unless I absolutely have to, unless I have no other option. And that is because that will increase the order of your QCL equation. It'll make it a little more difficult to solve. So try and avoid that if you can. All right, so since we know our configuration, since we know our GP, we can go ahead and get started with this first trial design. Let's try trial design number 1. Okay, so I'm going to write out the equation for the QCL, and this is for the standard configuration. Again, if you had an alternate configuration, this equation may be different. And as we write this out, you'll want to make sure that you know where this comes from and identify the pieces just so we can plug in. All right, so P sub P comes from our GP design right here. So the P sub P is 1 and the Q sub P is S minus 10. These are not going to change throughout all of our trial designs because they are given to us by the system assignment. Okay, P sub P is 1 and Q sub P is S minus 10. Okay, so the next pieces, the P sub P and the Q sub P, they come from our trial designs, and these are going to change. So the first one that we're going to try here is KC for PC, and for the Q sub C, that is going to be S squared. So let's plug that into our QCL equation, and that gives us a 1 times a KC plus an S minus 10 and S squared. Okay, so let's multiply this out. That's equal to a KC and S cubed minus 10 S squared. And even if we wrote this in the descending order, where we had S cubed minus 10S squared and then plus KC, we can see that we are missing an S term. So there's one clue that we cannot guarantee the stability here. Even if this were a positive 10, it's negative, so that's another reason this can't work. But even if that were positive, this term is still missing, so this design does not work. Again, there are 2 reasons. One is the necessary and sufficient condition here that is not held, and we're missing that term right there. Okay, so that's fine. It's sometimes the first trial design does work, not always there. Let's go ahead and try the trial design number 2. Okay, so QCL in this case, the trial design number 2 is this KC S plus A over S squared. So in this case, I'm just going to write them real small right here. My Q sub C is still equal to S squared, that's still in the denominator, and my P sub C equals KC times S plus A. Okay, let's plug those in, and we have a 1 times KC times S plus A plus the QP, which is S minus 10, we had it written up here, times the QC, which we wrote right here. All right, multiplying this out, we have KC s plus kca plus s cubed minus 10s squared. Okay, so things are getting a little bit better, and we could write this in the descending order where this term would be first, and then this term, and then this term, and then this term. But even if we did that, it doesn't change anything. This is still not held per the necessary and sufficient conditions. And then also, if we notice back here, we have no control over this anyway. It would be okay if it were positive in this case, and we could probably get this to work if that were the case. Yeah, so this doesn't work. And so let's try trial design number 3. Okay. And so the trial design number 3, we had that GC of S equals a KC S plus A S plus B over S squared. Okay, and then again, our P sub P is 1, Q sub P equals S minus 10, so we can just plug that into our QCL formula. So QCL in this case is going to be 1 times KC times S plus A times S plus B, and so this is coming from the numerator of the GC, plus S minus 10 from the QP, and then we have the QC S squared. Okay, so let's multiply this out, and it turns out we have KC times S squared plus A plus B S plus AB, and then over here we have an S cubed minus 10s squared again, and we can further multiply this out, having a KC S squared plus KC A plus B parentheses S plus a KC AB, and then these next two terms just carry down. Okay, let's write this in descending order so it's a little clearer about the necessary and sufficient conditions. Okay, so we have an S cubed that comes from here, and for the S squared term we have a KC that comes from here, and a minus 10 S squared. All right, for the S term, that is just right up here. So that's a plus KC A plus B, and that's times S, and then plus KC A B. Okay, so what we want to do here, it looks like we have a lot of control here, we have 3 variables, is test the necessary and sufficient conditions. Alright, so there are 3 necessary and sufficient conditions we want to talk about for a third order system, and if you work with all 3 of those necessary and sufficient conditions, you're good. Those come from Routh-Hurwitz again. I mean, aside from going through the whole Routh-Hurwitz procedure, I just happen to know the necessary and sufficient conditions, but you can do that if you're unfamiliar with it. Alright, so what we can do is just write these out. This has to be greater than 0, this coefficient. This coefficient as well has to be greater than 0. And the final test, the third condition, is actually that this coefficient times this coefficient has to be greater than the final coefficient here. So let's write that out. KC minus 10, and then KC times A plus B has to be greater than the final coefficient KCA times B. Okay, so if we look at these necessary and sufficient conditions, and if our problem statement is that we just have to find variables that work, this is not too bad. it's easy to find a KC that works with this, just anything greater than 10. And then again, as long as A and B are positive, if KC is anything greater than 10, of course that's positive. So this whole thing is positive, this whole coefficient. And then as long as you're careful in your values for KC and A and B, you can easily choose something where these multiplications are larger than this one. Okay, so for example, we could choose something like KC equal 40, A equal 4, and B equal 2. Now let's test that. If we plug in 40 here, and 4 and 2, then what we would get is ultimately, let's see here, 40 minus 10, and then 40 times 6 greater than 40 times 8. Okay, and then this becomes 30, and so we're left with 30 times 40 times 6. Is that greater than 40 times 8? And then we can cancel the 40s on both sides. And I can say that, yeah, 30 times 6 is greater than 8. So that does work. So these values work. And if we just needed to choose by the necessary sufficient conditions, then that should work. That's one example. There are many examples that work in that case. But what if we wanted specific roots? What if we wanted to set all the closed loop lambda sub I at specific values? We can do that, and I know I tend to choose real distinct values more often than complex values. I just want to make sure you know that you can choose complex values as long as you choose them in pairs. You have to have 2 or more of the lambda I. You have to have a system order of 2 or greater, and that should work. Just always make sure you choose them in pairs, and that should be fine. That should work. For me, it's just easier to choose real distinct values a lot of the time, or at least real values. So I'm going to do that here. And let's say, for example, we want all of the lambda I for the closed loop system at, let's say, -4, -1, and -2. Now, these had better be negative on the real axis. Otherwise, what are we doing? We're not stabilizing the system. We're making it unstable. We don't want to do that. So make sure that these are in the left-hand plane for the real axis part. Okay, so let's just set up the equations. We won't actually solve for the values, but let's set up those equations. So what you would want to do, if these are the system roots that you want, let's multiply that out. First, we want to get that model characteristic equation. So model system characteristic equation. And think about it in a factored form. So our first root is -4. So I'm going to write lambda plus 4. Think about this, solving this part of the equation would give me the root. So you add 4 right there. Lambda plus 1, because our second root is a -1. And our third root is a -2, so we're going to be lambda plus 2 for this last part. And that, think about that as set to 0. So we'd be solving and finding those roots. And I'll just write the roots right over here again. Okay. All right, so multiply this out. And if you do multiply this out, you should see that we have a lambda cubed plus a 7 lambda squared plus 14 lambda plus 8 equal 0. All of that's just FOILed out. It becomes this. And so, at this point, what you would do is compare the coefficients with our QCL for our design that we decided would work. Okay, and let's set up those equations. So just referencing this sheet right here, what we have see, order to order, matching that up, we'll have KC minus 10 equals 7. KC times A plus B equals 14. And then our third equation would be KC times A times B equals 8. Now we would solve these equations. KC, A, and B. Now on a quiz or a test, normally I would have asked for you to just set up the equations. If you're doing homework, then it's a little easier to have access to something like a program, or maybe MATLAB or calculator that can solve a bunch of equations at once. There are also web pages that do that. So that's a little easier. You can actually get real values at that point. And then ultimately the answer to this problem we found 2 different sets of gain values, or at least we set up the equations for the second set. You would only need to solve for one, depending on what your problem is. And then we would just, at the very end, plug in those values and state what our G sub C design is. And it turns out that trial design number 3 was the one that we went with. So whatever those values are, you would plug them in here, and then that would be your answer for this specific problem. Now, just to follow along, if you look back at the problem when we started, we did this problem with tracking a command signal. So at this point, let's re-examine and see, what if we had a disturbance in here? How would this problem change? And it would take a substantial disturbance, actually, to change this problem. So we would need a disturbance of, let's say, t squared, or something like a constant plus a bias term, constant plus ramp term, something like, and I was pointing to the wrong one. This is the bias, this is the ramp term. Or maybe, let's say, this one would make a difference, and what I'm saying here is we could accommodate this one, just a constant by itself, or a stepwise constant. So to draw that distinction, these disturbances require 1 or 2 free S's, but no more. So since they are within the range of free S's that we are designing for, our design is still valid. So we can already accommodate with designing for 0 disturbance. We can already accommodate all of this range of disturbance. Okay, it would take a disturbance of this strength, or perhaps a constant plus t squared, or perhaps constant plus a ramp plus a t squared, something like this. And let's go ahead and stick some constants in there just because we don't know. Something like these ranges, where you would have to differentiate the disturbance signal a total of 3 times to be able to get it to go away structurally. And so that is the difference. That is when do we have to change the design? Well, when we need more free S's to accommodate a disturbance, if that's what's being added to this problem.